All right, all. Today we're going to get the RSA encryption algorithm, the kind of light on math version. So there'll be a separate video that you can get the slightly heavier on math version. I promise for anybody who hasn't had a fair bit of number theory, this may well feel heavy on math, but I promise this is the light on math version. All right. So here's essentially how the RSA encryption algorithm works. Step one, we need to choose a pair of big primes. Okay, I'm going to call those primes P and Q. And then we're going to, step two, we're going to calculate N, which is going to be the product. So that's going to be P times Q. All right. Then N here is going to be half of the public key. So our public key is going to be two numbers that we're going to get out. The first number is going to be N, the other one we'll get to in a second. All right. Then for step three, we're going to need to calculate something called the totient of N. So this phi here is the totient. This is a special function. You can go check out the math heavy version for what this function means. But in our case, this is going to be P minus 1 times Q minus 1. Then for step four, after we've calculated the totient, we're going to pick two numbers, and those numbers are going to be D and E, and those are going to need to be picked. They're going to need to be picked in kind of a specific way. So E needs to be relatively prime to the totient. So needs to be relatively prime to our totient of N. What relatively prime means, so this phrase here, relatively prime means they need to share no factors. Or at least share no proper factors. Everything shares one as a factor, right? But they need to share no proper factors. So the biggest thing that needs to divide both of those numbers is 1. And we need that D times E is equal to some number k times the totient of N plus 1. And in practice, the way we're going to do this is we're actually going to pick k's, and then, or at least the way I'm going to do this in practice with my easy example is I'm going to pick k's, I'm going to take those k's, multiply them by the totient, add 1, and then I'm going to factor that number and go until I find a convenient pair of D and E. There's other ways to do that, like picking D and E is a like kind of subtle-ish process. There's a number of different algorithms that you can use to get D and E. I'm gonna do a like relatively easy kind of guess and check thing because I'm like basically making a toy here, right? I'm not gonna make any of my numbers big enough to actually use. If you want to make your numbers big enough to actually use, well, you're gonna probably have to do some like, I don't know, actual math, and I'm just not gonna do that. So I got step 4 here that I picked D and E, great. And now my next thing I'm going to do is we're going to pass out N and E as the public key. And I guess I should note here that E is the second half of the public key. and then we're going to need to talk about how to encrypt and decrypt. I'm going to do an example of this in a minute, so let's just scroll down in here, and I'll give encryption and decryption steps. Encryption is the slightly more complicated one. So to encrypt a number, I'm first going to convert my message into some kind of number. I'm going to call that number M for message. How you do that is like itself a relatively complicated process. You might, for instance, do something like, just as an example, you might like make the letter A into 0, 1. You might make the letter B into 0, 2. That'd make the letter Z something like 26. And then if I wanted to spell a word, right? Like if I wanted to spell abs with a Z, right? I'd think A, B, Z is going to turn into 0, 1, 0, 2, 26. And then I could do stuff with that number. That's not the only way to do this. There's a huge, huge number of ways to do this. The more you kind of scramble the message before you turn it into a number, kind of the harder this is going to be to decrypt. But most of it isn't in this ciphering process here. Most of it's going to be in the actual encryption process. So like somehow you convert your message into a number. Bunch of ways to do that. One way you could do it is you could just pull it out of the RAM, right? In the RAM, it's kept in there as binary. You could just yank it out of the RAM and then encrypt it straight from there. That would work. Step 2 is you're going to calculate C, which is going to equal the message raised to the encryption exponent modulo n. So n, remember, is my p times q. That's one of the things I passed out as my public key, right? Up here. That n there is half my public key. So here they've got their message raised to 1/2 of the public key, and then they've modded it by n, which is the other half of the public key. And then they're going to send C. That's going to be the encrypted version. Okay, to decrypt, decrypting's pretty chill. So we're going to get C, right? We're going to compute or calculate. And the thing we're going to calculate is C raised to the D. D is our decryption exponent. So we're going to take the message that we got from them. We're going to raise it to the D power. And then we're going to mod that by n. And the fact that we've been able to mod that by n is going to actually just result in getting our message back. And then we're going to unconvert. So we're going to convert M to our message. And then, I don't know, step 3, like profit or like take over the world or like whatever, right? Okay, so let's try this with some numbers. This is, I'm going to try this with small numbers. I'm still going to need a calculator. So a pair of big primes. I'm going to pick medium primes. So I'm just going to do this off to the side here. Let's see. I really want a purple. All right, so we're going to do this over here in purple. So I'm going to pick P is going to be, let's see, let's pick P as 17. Let's pick Q as 23. So that means that N, right, so we chose these. Looks like a weird spelling of the word choose. Okay, so we choose P and Q, and then we calculate N. N in this case is 391, I think. Let's go get a calculator. So to get a calculator, I did find that the usual calculator I would use for something like this, Desmos, did not appreciate this. So I'm going to just get this side by side here and arrange this a little bit. All right, so I've got my little setup going. Okay, so I just want to know what 17 times 23 is, so we're going to just confirm that over here. We're going to get 391. Great, cool. All right, next, we need to calculate the totient, which is p minus 1 times q minus 1. So that's going to be us here. We're going to calculate, and we need to calculate totient of n is going to be 16 times 22, which in my case here happens to be 352. And then we need to pick D and E that are relatively prime, and they need to satisfy this equation. Okay, so I need D times E to be some number times 352 plus 1. So here's what I'm going to do. I'm going to try k equals 1. So that would have 1 times 352 plus 1 needs to be D times E. So if I go over here and figure out 352 plus 1 is 353, and I want to know what the factors are. So I'm just going to ask Wolfram to factor 353. And it's telling me 353 is prime. So the only numbers I could pick for D and E are 353 and 1, which isn't going to work. So for me, this k was not a workable value, so I'm going to try k as 2. So I want to factor, and the number I need to factor is going to be 2 times 352 plus 1. Oops, not plus bam. That's not going to work. Jeez, Joe, learn to type. All right. Okay, so I got that it's 3 times 5 times 47. So I can do 15 times 47 can be my workable number. For k is 2, we got 705. And we can say, all right, so D is 15 and E is 47. Now, these numbers aren't really that big. This would be actually way too easy to break in practice, but we can play with our toy. So now what we need to do is we can pass out N and E as our public key, right? So here we can say public is N is 391 and E is 47. And now if somebody wanted to break our encryption, they would need to factor N into its 2 prime factors, and then they would need to try to find our K and try to thereafter find D. Now, it's pretty possible there's multiple values of K that might work, which would result in having different values of D and E. So that's an upside for us, right? They may have to wade through a bunch of different options here. Really, what makes this algorithm work is that it's pretty hard to factor big numbers. It just takes lots of time. So when we ask them to factor those 2 big primes that we multiplied together at the beginning, it's going to take a bit. That's going to take long enough that our credit card's going to expire before they find out what the information was, or before they find out the number. That's really basically all of how this works. So let's see if we can encrypt something. So let's convert a message into a number. So I'm going to say that my M is going to be the number 7, just to keep numbers small and manageable, right? So then I'm going to calculate. I'm going to pick my message to be 7. And then I'm going to calculate. And the thing I have to calculate is going to be my message raised to the encryption thing. So we're going to do 7 raised to the 47. And then we need to mod it by 391. So over here, I'm going to do 7 raised to the 47 mod 391. I'm going to get 90. So this is 90. That's my encrypted message. And then if I want to decrypt my message, so we're going to send 90. And then to decrypt, sorry, that was C, the encrypted version. To decrypt, right, we're going to take our 90, we're going to raise it to the 15th power, that's our decryption key, and then we're going to mod that by 391. So over here we need to do 90 raised to the 15th power mod 391, and I got 7. So that worked. We got our number back. So M is 7. That's what we picked as our message earlier. So this is basically us working. So this is roughly speaking, like, actually, not roughly. This is exactly speaking how RSA encryption works. The thing that I've glossed a little bit is the math behind how it works, but it does just work. Like, there's a little bit of number theory to it. It just works. What makes it effective is basically that it takes a long time to factor this number n into its 2 prime factors. 391 is going to take milliseconds. You need to pick big-ass prime numbers for this. Just absolutely fuck-off huge ones. And then after you've picked your absolutely fuck-off huge prime numbers, then you can pass out n, and it's going to be quite hard to break that. And remember, these are one message going forward and back, and then afterwards we're going to pick another pair of big-ass prime numbers. Relatively straightforward, right? We can vary our D and E as well, right? Like this happened to work for K is 2, right? But if I pull my Wolfram back up here, and I say, all right, let's go back and try, let's try to factor some other version, right? So let's factor, say, 3 times 352 plus 1. Dang it. I did it again. Okay, so this one, if we picked K as 3, would give us 2 prime factors, 7 and 151. That's probably not great, but those would work as a pair. When we do 4, we get a prime number. When we do 5, we get something factorable again. Great. Like those aren't great numbers to use. Okay, 6 doesn't give us anything like really useful. Okay, 7 gives us a nice combination. So we could use 5 times 17 and 29, right, as an option for our D and E. Those would also work. That would be kind of different encryption, decryption pairs. Same N, works the same. Like that would be another option. This is actually really kind of the guts of most encryption that we use. Most encryption that's actually on the internet these days is some kind of base, like at the bottom, it's RSA encryption more or less, which is cool. And it's not that hard. It's relatively easy to write. You could write this by hand if you really wanted to. You could kind of work around with your converting messages into numbers, like adding a cipher there can make things take a bit longer, can make things harder to decode. That's a very valid place to add some difficulty. There's a bunch of other ways to do encryption, right? You can scramble encryption a ton of ways. So you can always encrypt a message first and then send it using RSA encryption and then decrypt the RSA and then decrypt it again. Layering encryption can be a really interesting way to avoid exposing data. This, by the way, is like roughly the same thing that powers encrypted messaging apps like WhatsApp or Signal. Those kind of things are powered in a similar way. Thank you guys for watching. I will catch you on the next one.